Hello, and here we have the walkthrough for the GCSE Combined Science Trilogy Foundation Tier Physics Paper 2. Question 1 is about magnets and magnetic fields. Figure 1 shows there's a magnetic field around a copper wire carrying a current, so as we know, any current carrying conductor will create a magnetic field. And the first question asks us, what do the arrows on the magnetic field line represent? And it's simply the direction of the magnetic field. So you might also see bar magnets with north and south poles, and you just need to remember that the magnetic field always goes from north to south, kind of like that. Next, complete the sentence. As the distance from the copper wire increases, the magnetic field's strength decreases. So the further you are from the wire, the weaker the magnetic field. Uh, 1.3. Suggest how the field lines on figure 1 show the variation in field strength. So it's the distance between the magnetic field lines that tells us how strong it is. So the closer together the field lines, the stronger the magnetic field. 1.4. We have a student coiled the copper wire a different number of times to form a solenoid. So a solenoid is literally just a coil of wire. Each time the student measured the strength of the magnetic field inside the solenoid, and then he drew this graph, and it's asking us to draw a line of best fit. So obviously you're going to use your ruler and a nice sharp pencil. Again, if in the exam your pencil's not sharp, you need to put your hand up, ask for a sharp one. So looking at our line of best fit, you need to have the line as close to as many points as possible, and you need to have an equal number of points above and below the line. So I've got one above, one below, and one kind of one down there, but that should be fine, so we'll be happy with that one. Determine the increase in the strength of the magnetic field when the number of turns on the coil is changed from 12 to 18. So we're going to have to use our graph again. So we're flipping back the page. We're going from 12 to 18. So 10, 11, 12. So each two squares represents one turn on the wire. Draw your line up and across. And that looks to me to be at 0.9 arbitrary units. Next we went up to 18, so 15, 16, 17, 18. Let's draw a line up again until we intersect with the graph, and across. A bit wonky. That looks to be 1.4 arbitrary units. So if we go back over, we need to go 1.4, our final value, minus our initial value, which was 0.9. And even though we could probably do this in our heads, we'll always put it into the calculator. So that's an increase of 0.5 arbitrary units. And make sure we write it here. Underline it and move on to the next one. How could the strength of the magnetic field be increased? So we can either increase the current through the solenoid, and the way we'd increase the current through the solenoid is by increasing the potential difference. So we're going to tick those two boxes. Change the temperature, that's not going to help anything, probably make it lower. If we spread the turns of wire on the solenoid further apart, again, that's not going to help. And using a high resistant wire, that would actually decrease the magnetic field strength as well, because it would lower the current. So it's not going to be that one. So next we have a solenoid. So as we mentioned earlier, it is just literally a coil of wire. It tells us that this is going to be the north part, this is going to be the south, and it's asking us to draw field lines. So we have to draw the lines that come out, go around, and come back in. Just like this. Now if we wanted, we could draw the lines inside the solenoid and they'd just be straight uniform lines that were parallel to each other, but I don't think we have to do this in this situation. What we do have to do is put arrows on, and we mentioned earlier that the field lines go from north to south, so our arrows will go like that. Point to mention, make sure your field lines don't touch. So the field lines should never touch. So mine are a bit wonky here, but at least they're not touching. How can the solenoid be made into an electromagnet? All you need to do to turn a solenoid into an electromagnet is to put in an iron core. So we add an iron core. So we take a cylinder of metal, something like a nail or something like that. We could slide it inside that core, and the iron core would become an induced magnet, hence an electromagnet. So question 2 looks at radiation, and first activity is to complete the sentences using the answers from the box. So X-rays, which are part of the electromagnetic spectrum, travel at the speed of light. So any electromagnetic wave will travel at this speed. Just for information, is 3 times 10 to the 8 meters per second, or 300 million meters per second. X-rays can cause cancer because they are ionizing, so they can collide with the atoms in your cell, knocking off electrons, turning the atoms into ions, which can be damaging to your DNA, which can lead to cancer, which is not good. 2.2, how do X-rays compare with gamma rays? So gamma rays are the most energetic and have the highest frequency, so we're looking for something with a higher frequency, so it's either going to be this one or, beg your pardon, X-rays have a lower frequency, so it's either going to be this one or this one. If you've got a low frequency, you're going to have a longer wavelength, so it's going to be this one. So next question shows us some results from an experiment that's somewhere where they measured the radiation dose at different distances from the machine. So they increased the distance, they measured the dose of radiation, and as you can see, the further away you are, the less the radiation. It's asking us to calculate a mean first, so we'll add these together. So 0.039 plus 0.035 plus 0.040, and we'll divide that all by the number we have, which is 3. So 3 readings we divide by 3. Take your calculator. So you'll either need to use brackets or be careful where you press equals. So I'll use brackets this time. Close brackets divided by 3. If you don't use brackets or you don't press equals, all you're going to be doing is adding these two numbers together and then dividing this number by 3 and adding that, so that will give you the wrong answer. So to make sure you use brackets, and that gives us 0.038, and again we'll write it down here, millisieverts. What conclusion can be made from the results in table 1? Well, we kind of mentioned that earlier. So as we increase the distance, the dose went down, so that's what we're looking for. So the dose decreases if you stand further from the machine. Very good. It's certainly not directly proportional to distance. The dose is not the same at all distances, and there is not a linear relationship, so it's not a straight line. So yeah, definitely happy with this answer. An X-ray gives a radiation dose of 0.180 millisieverts. Natural sources give a dose of 0.012 millisieverts, so a lot less, but that's in 1 day. So we need to calculate the time it would take to get the same amount of radiation just from natural causes or natural sources to make up that 100.180 millisieverts. To do that, we just see how many times this goes into that. So we do 0.180 divided by 0.012. See what we come out as. Always use your calculator. 15. So it would take you 15 days to reach the same amount of radiation as a single X-ray. Suggests why doctors use X-rays even though this increases the risk of cancer to the patient. So the benefits of using the X-ray outweigh the risks. So if they didn't have the X-ray, they might not find out what was wrong with the person and they could become severely ill. Whereas taking a few X-rays, even though it will increase the risk of cancer, it's only going to increase it by a small amount. X-rays can also be used to treat cancer. A patient receives a dose of 20 millisieverts for an X-ray. Proton beam therapy only delivers 40% of this dose. So we need to work out what 40% of this number is. So we do 40, which is our percentage, divided by 100, because it's a percent, so it's per 100, and then times that by our initial dose. So 40 over 100 times 20 gives us 8. Millisieverts, and again, jot your answer down there and underline it for the examiner. Question 3 shows a roller coaster train as it's pulled up a slope on a track. So we need to, the arrows A, B, C and D represent the forces acting on the roller coaster train. So we have D acting downwards, that's obviously going to be its weight due to gravity. You're going to have C, some sort of resistive force such as air resistance or friction. B, this acts at right angles to the surface, so that's probably going to be the normal contact force or the reaction force. And the force A, pulling it upwards, is just going to be the machine pulling the roller coaster upwards, so thrust perhaps. Give 2 ways that the force arrows show that the forces are vectors. So vectors have both magnitude and direction. If it were a scalar, it would only have magnitude. So our arrows have a magnitude, which is represented by the length of the arrow, and they also have a direction. Which arrow shows the weight of the roller coaster train? We just talked about that a second ago. Let's have a look at the diagram. So it's acting downwards towards the centre of the earth, so D is going to be the weight due to gravity. Put that in there. Which arrow shows the normal contact force? We're looking for an arrow that's at right angles to the surface. So a normal line is at right angles to the surface or the boundary. So if we flip back over, this one is at right angles to the track, so B is going to be our normal contact force. Figure 5, so we have a graph to interpret. It shows the magnitude of the acceleration of a roller coaster during the ride. And again, it looks a bit confusing at first, but once you read through and try and interpret what's happening, it's not too bad. So on the y-axis over here, we have the magnitude of the acceleration, so the size of the acceleration. It doesn't tell us the direction, only the magnitude. And on the bottom here on the x-axis, we've got the time since the start of the ride. And as we can see, you have some small accelerations towards the start, then no acceleration, where it's probably travelling at a constant velocity, acceleration increases, then another constant velocity, and then a big acceleration in the middle, and then a few more smaller accelerations towards the end. So why has a line graph been drawn instead of a bar chart? So if we look at our data on the y-axis, we have numbers. So these values can take any value. So we call these continuous. So essentially, if they're numbers, we can say it's continuous if we simplify it. And on the x-axis, we've also got numbers. Now, if we had labels instead of numbers, so if we had things like blue eyes, brown eyes, grey eyes, that would be discrete data. But because it's numbers, because it can take any value, we'll call it continuous. So we're looking for continuous. Here we go. Both variables are continuous. They do try and throw a categoric, which is a different way of saying discrete, down the bottom there to try and catch you up, but it's definitely not these ones. What conclusions can be made from figure 5 about the motion of the roller coaster between 10 and 15 seconds? There's zero acceleration here, so if there's no acceleration, there's no change in speed, so it is moving at a constant velocity. Uh, 3.6, what's the maximum acceleration of the roller coaster train? Let's go back to the graph. So the peak is clearly here. So let's get our ruler and our pencil. Nice and sharp. And draw a line across from the tip of the crest to here, and made it a bit wonky, but I'm pretty sure that should come out as 24.5 meters per second squared. So we'll flip back over. Maximum acceleration 24.5 meters per second squared. The maximum safe acceleration for most people is 5 times the acceleration due to gravity, and it's given us g here, it's given us the acceleration due to gravity. So if we want to know the maximum safe acceleration, all we have to do is 5 times g. So 5 times 9.8 is 49. And the acceleration is meters per second squared. Now, it's asking us to explain whether the acceleration is safe. So we can endure this much acceleration, so 49 meters per second. The train only gives us 24.5. So 24.5 is a lot less than 49. Don't forget units. So train is safe. So they might do that plenty of times in your exam, ask you to make a calculation, make a comparison, and then decide whether or not you agree with the statement or disagree with the statement out there. Last part of question 3. One of the passengers on the roller coaster train has a mass of 58 kilograms. Calculate the maximum force experienced by the passenger during the ride. What we've just said is mass was 58. The acceleration, we're going to have to go back to the previous page. So you've just worked out the acceleration. It was this 24.5. So you might have to keep going backwards and forwards within the question to look for numbers sometimes. So what did we say? 24.5. So let's write our equation down here. Substitute in our values. Get our calculator. Is 1421. So 1421. The unit for force is the Newton, so newtons. And again, we'll write it down here, 1421, and the unit newtons. We can use a capital N if we wanted, that would be fine. A lowercase n, however, would not be fine, so make sure you do use uppercase N. Okay, moving on to question 4. It starts with a picture of a guy in a wheelchair. And the first part of the question says the wheelchair moves at a constant speed of 2.4 meters per second for 4.5 seconds. So this is a speed, this is a time. Calculate the distance moved by the wheelchair. So it's given us distance equals speed times time. They've been very nice here. So distance equals speed times time. The speed was 2.4, time was 4.5. Get the calculator. 2.4 times 4.5 gives us 10.8. So 10.8, and it's meters. And again, when you're doing calculation questions, it's always good just to check that they're not asking you to give it to a particular number of significant figures. So I'm going to leave mine at 3 sig figs, but they might ask you to give it in 2, whereas you'd have to round it to 11. What could a reason be for the speed of the wheelchair decreasing? So why might the wheelchair slow down? Well, let's look at our options. So if you start going downhill, well, normally when you go downhill you get pulled down by gravity, so you start to speed up. So I don't think this is going to be the reason. It starts going uphill, so if you go uphill you're working against gravity, that might well slow you down. Let's see what the other options are. Its store of kinetic energy has increased. So kinetic energy is the energy of an object due to its motion. If you increase the kinetic energy, it's going faster. So no, it's not this. And it's used more power from its battery, so if you use more power, you're getting more energy through, you're actually moving faster, so it's definitely not that. Yep, the only thing that would slow a wheelchair down would be the fact that it was going uphill. Next, a student measured how the distance travelled by the wheelchair changed over time, and they plotted a graph. So this is a distance time graph. So on the x-axis you've got time, distance on the y-axis, usually in seconds and meters, but they haven't given us units here. If you have a straight line, that represents a constant velocity. If you have a straight line with a steeper gradient, that means it's travelling faster. So B is moving faster than A. If we go up to this section C, you can see it's a horizontal line, so the distance hasn't changed during this time. And if your distance isn't changing, then you're obviously stationary, you're not moving. And then starts off again, and D, he's moving very quickly, because we can see that this line, the slope of this line, is steeper than the previous two down here. Here we go. In which section of the graph, A, B, C or D, did the wheelchair travel fastest? So if we look here, D, that's where the gradient is steepest, that's where the slope is steepest. We can say D. So the gradient of section D was the highest, or the steepest. Next question, the student used a data logger, so it had a sensor that it could plug into a computer that would take automatic measurements, and these are good because they're more accurate, so you're removing any possibility of a human mistiming something, so they're more accurate, so they get closer to the true value, and they can record values more frequently. So they can measure the speed or the distance travelled as many times as you want, hundreds of times a second if you need it, and that's very good to paint a picture of exactly what's happening in an experiment. We have another graph. This time, instead of looking at time and distance, it's looking at time and velocity, so speed in a given direction, and the sketch graph shows how the velocity changes. It increases its velocity at first, and then as it gets faster it starts to slow down until we reach this point here. We're at a constant velocity, so there's zero acceleration here. The forward force on the wheelchair is constant as it accelerates on flat ground. Which force reduces acceleration? So just looking at these, I think I know what the answer is, but we'll go through all of them. So air resistance is a resistive force, so that does slow you down, so it could be this one. Magnetism, I don't think magnetism is going to play a major part in this, that doesn't sound right to me. Tension is the force in a rope or string or a piece of elastic or wire, There doesn't seem to be any rope involved. We're not tying the person up, so I'd say it's not the tension. Weight acts downwards, so it's not going to be a factor on flat ground. So if you imagine that's flat ground, here's our wheelchair, weight's acting in that direction, it's not really going to influence our motion horizontally because it's at right angles to that motion, so it's not going to be weight. So yeah, air resistance again sounds like the best option. Explain the acceleration of the wheelchair at point A. So it's at constant velocity. So the acceleration is 0. It's not changing velocity. This means there must be no resultant force. So no resultant force at all on the wheelchair. We could have forces acting, so for example there might be air resistance, so there might also be the driving force of the wheelchair, but they'd have to be equal and opposite and they'd cancel each other out, so we'd have no resultant force. Next we've got a calculation. So a wheelchair starts from rest, it accelerates at a constant rate until it has a speed of 1.5 meters per second. So this is going to be one useful value. So that's going to be its velocity at speed at the end of the question, so I'm going to give that the symbol V for final velocity. Again, it's always helpful to annotate your question like this. And the wheelchair starts from rest, so if it's at rest it's not moving, so that's our initial velocity, and it's going to be 0 meters per second, and we'll give that the symbol U. The wheelchair travels a distance of 2 meters, so that is a distance or a displacement, and we give that the symbol S. So displacement, and we have to calculate the acceleration, which is the symbol A. So we're looking for something that has an A, a U, a V and an S in it. And with these acceleration questions it's really helpful to put this down the side and then you know exactly what you're looking for. And this bit is really important. I'm going to highlight it, it's that important. Not sure if that's helped you see that, but it's asking us to use the physics equation sheet. So if it says that, use the physics equation sheet. Try and find an equation that has some of these letters on, and if we look at it we'll see the one we're looking for is v squared minus u squared equals 2as. So final velocity minus initial velocity equals 2 times acceleration times distance. That's good. So we've got our values down here. So our initial velocity was 0 meters per second, final was 1.5 meters per second, the distance we travelled was 2 meters, and our acceleration is, that's our question mark, that's what we don't know yet. Let's put our values in. So 1.5 squared minus 0 squared, it's good to have a 0 because it means we can ignore it, equals 2 times the acceleration, which is our unknown, times by s, which is 2.0. So we can simplify this a little bit. If we're taking 0 away from anything, we don't care about that one. 2 times 2 is 4, so we're ending up with 1.5 equals 4, so 1.5 squared equals 4 times the acceleration, and we can bring the 4 down underneath to give us 1.5 squared over 4 equals our acceleration. So 1.5 squared divided by 4 equals 9 over 16, 0.5625, and its acceleration, so it's going to be meters per second squared. And I know that it hasn't asked us to give it to a particular number of significant figures, but just looking at my values up here, these are both the 2 significant figures, so I'm going to round this to 2 significant figures when I write it down here. so 0.56 meters per second squared. Moving on to question 5, we've got figure 9. It shows a cyclist over here towing a trailer with a load on. And question 1 asks us to describe how Newton's third law applies to the force between the bike and the trailer. So the bike is going to be pulling the trailer with a force something like that, and the trailer is going to be pulling the bike backwards in an equal and opposite direction. So the bike pulls the load, or the trailer, with a force that is equal in magnitude but opposite in direction, to the force with which the trailer pulls the bike. So a bit of a long-winded response there, but key points to remember are, so equal in magnitude, opposite in direction. So Newton's third law states that any action has an equal and opposite reaction, so any force you apply, there will always be an equal and opposite force that acts against it. Next, 2.2, student investigated how the stopping distance of the bike was affected by the mass of the load. So the same person rode the same bike through the investigation, give two other variables that should have been controlled. So again, it's always important to make sure our control variables remain constant and to make sure our investigation is valid. So to make sure it was valid, to make things a fair test, the cyclist would have used the same trailer, he would have used same weather conditions, same road surface or same gradient, or the same speed. So I've written quite a few down. You guys only really need to choose two. If it's a 2-mark question, you need to give 2 reasons, and it even says 2 here. So you pick any 2 of these 4 and you'll be fine. Next we have the results of the investigation. So it seems clear that as you increase the mass of the load, our stopping distance increased in proportion with that. So there's a linear relationship essentially, and it's asking us to draw a line on figure 10 to show how the stopping distance would be different if a heavier cyclist rode the bike. So we need another line, and because it's heavier, it's going to be harder for it to stop, so it's going to have a larger stopping distance, but it'll have a similar gradient. So I'm just going to whack my ruler here. Brilliant. So bigger mass means bigger stopping distance, and obviously we're increasing the mass further by adding more to the load as well. Last part of question 5.4. At one time in the investigation, the cyclist was distracted. The distraction increased the stopping distance of the bike that did not affect the braking distance. So the reaction time of the cyclist would increase. So he's distracted, so it takes him longer to register a hazard or realise he has to stop, so his reaction time's gone up. This means he would travel further before pulling the brake. So essentially our thinking distance has increased. So let's put that as well. And the stopping distance is a combination of both thinking distance and braking distance. So question 6 looks at the ripple tank experiment. So here's the equipment. You have a lamp overhead shining down on the hot apparatus. You have some water in a shallow tray that has a transparent bottom. You have a motor and a vibration bar here. So the motor spins around and it makes this bar vibrate against the water, and that causes waves to travel from one side of the ripple tank to the other. Now the lamp shines down through the waves and through the transparent bottom of the ripple tank onto a piece of white card underneath, and that gives you a nice really clear pattern of the waves underneath. So you can see that essentially the peaks are represented here, and you can quite easily measure the distance in between the peaks. So let's see what it asks us. So the motor makes a noise. So this appears to be a sound wave when it is turned on. Describe the differences between the properties of the sound waves produced by the motor and the water waves in the ripple tank. So let's start with sound waves. So sound waves are longitudinal, which means they vibrate parallel to the direction of wave travel. They also have compressions and rarefactions, but we'll leave that for a different question. Water waves are transverse. So transverse waves vibrate perpendicular at 90 degrees to the direction of wave travel. This is almost certainly going to come up, so it's very important that you remember longitudinal waves vibrate parallel to the direction of wave travel, and water waves, transverse waves, vibrate at 90 degrees to the direction of wave travel. It's not good enough to say they just vibrate at 90 degrees. You have to say 90 degrees to the direction of wave travel. You need to say what it's at 90 degrees to. Now obviously above, it's the same with parallel here. The period of the sound waves produced by the motor is 8.3 milliseconds. So I can see straight away they're trying to catch us out. So this milli means to the minus 3. So that's like saying 8.3 times 10 to the minus 3 seconds, or 0.0083 seconds. To do the conversion, we can get our calculator. Milli is always divided by 1000, so 8.3 divided by 1000 gives us 8.3 times 10 to the minus 3. And it's asking us to calculate the frequency of sound waves, and hold on a second, something important. Use the physics equation sheet. So we're looking for something with a frequency f, and it's given us a period which will be a big capital T. So you'll find the equation will be frequency equals 1 over time period. So we have to do 1 over 0.0083, and let's see what it comes out as. 1 divided by 0.0083 gives us 120.48. The unit for that's going to be hertz, and I'm going to round it just to 120 hertz down here. I think that should be fine. So 120 hertz. So the last question is the 6 marker. So it's asking us to explain how a student can make appropriate measurements and use them to determine the wavelength of waves in a ripple tank. There's 2 ways of approaching this, and I think the exam board want us to do it a particular way. So the equipment we're going to need in addition to the ripple tank, we're going to need a stop clock, stopwatch, timer, whatever you want to call it, and a meter ruler. First thing, we need to measure frequency. And frequency is waves past a point in 1 second. So it's difficult to count the number of waves that go past in 1 second. So the best thing to do would be to time how long it takes for 10 waves to go past. So if you can imagine the waves are going past one at a time, so you'd count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop your stopwatch, and then you do the equation frequency equals number of waves over time taken. So now we've got our frequency. Next thing to calculate is the speed of the wave. So we measure the distance travelled by a wave in a particular time. An easy way to do this might be just to time how long it takes the wave to go from one side of the ripple tank to the far side, and then measure the distance to the ripple tank. Once we know the distance travelled and the time it takes, we can just use the equation speed equals distance divided by time. That's going to give us our speed. The last thing we do, so we need to work out wavelength, or sorry, wave speed. No, wavelength, that was right first time. So wavelength, we simply calculate using the equation wave speed divided by frequency. So we've already calculated wave speed, we've already calculated frequency, plug it into here, and that's our value for wavelength.